So how do we go about analyzing the kinetic data? In other words, we have this raw data from an experiment. How do we get those useful parameters like Km and Kcat out of it? So let's say, for example, we had some reaction that we monitored. It was under both initial velocity conditions, so substrate was way greater than product, and also steady state conditions where the concentration of substrate was way greater than the amount of enzyme, so just a small amount of enzyme in the reaction. And then we measured the rate of appearance of product. In other words, we looked at initial velocity. How do we determine Kcat and Km? And so we would have had some, like we mentioned before, some series of different substrate concentrations, and that would have resulted in a series of initial velocities that we would have had from that. So we have this table of data, essentially. And a couple things we could do. We could use a nonlinear curve fitting program on the web or a standalone program where it would you would input the different velocities and the different substrate concentrations, and it would determine or fit the parameters Vmax and Km. This is how we do it most of the time in the laboratory, and every time you see a modern biochemistry paper that uses reports Km or Vmax or Kcat, this is how they did it. You will actually do this as part of the homework set, so you will get to experience that a little bit. Another thing you can do is to manipulate the variables so that we convert that curve into a straight line. In other words, we want to linearize the data. And this is accomplished by looking at the reciprocal of each of those variables. So rather than looking at initial velocity as a function of substrate concentration, we look at the reciprocal of the initial velocity as a function of the reciprocal of the substrate concentration. What we would observe is the data, rather than forming a hyperbolic curve, should anyhow, if the data are good, form a line like this. So if I have, say, 5 data points, they would look something like that. And I could, that's something that you can easily do in a program like Excel, fit a line to that. It's even something you could do in the old days before you had computers. You could use graph paper and extrapolate this line. So we'd fit a line to these data, something like that. Hopefully your lines are a little straighter than mine. And there are some important features here. The first one is that this intersection point right here, notice that is on the y-axis, and so it has that intercept has units of inverse velocity. In fact, that value there is the reciprocal of Vmax, 1 over Vmax. And so if you determine what the y-intercept is of this sort of data, you can then take the reciprocal of that value and you will have the Vmax of the reaction. Likewise, the intersection down here at the x-axis, look at the units of that, would be inverse molar. And so this actually is related to Km. It's negative 1 over Km. So to determine Kcat from this sort of data, you would be able to find Vmax, and then using the equation that we looked at before, determine Kcat from that. So just a couple things about this. This is actually a relic from an era long ago when, like I said, they would use graph paper and rulers and things like that. It's actually not the most reliable way to determine these values because, for example, you have data up here and you're trying to get a parameter way over here, right? So small errors here can be magnified into large errors down here, and so that extrapolative nature causes this to be very error prone. So we don't really use this to determine Km and Vmax. We use those nonlinear curve fitting programs. But we do use these plots because they demonstrate important trends that we're going to look at that are a little harder to see in a Michaelis-Menten plot.